All right, so here is our final unit, Unit 12, that has to do with radioactivity and nuclear processes. Okay, so what is a radioactive nuclei? Well, it's remember, nuclei is just the plural for nucleus. So a nucleus is unstable. Nuclei would be the plural. Radioactive nuclei are unstable. They undergo spontaneous changes and emit energy. When they undergo these changes, they emit energy, and they shoot this energy out of the nucleus, and in the process, they become more stable. Okay, so just a little background. Henry Becquerel was one of the first people to discover radioactivity. He had uranium near some photographic plates, and he noticed that the photographic plates were exposed by in sort of a foggy look to it when they were near the uranium. And then you've probably heard of Madame Curie and her husband, who also did a series of investigations into radioactivity and mostly studied radium and uranium also. Now, one thing that I want you to keep in mind is that the rate of radioactive decay is not affected by normal factors that we have learned about before. So the temperature, the pressure, the amount that you start with, the type of the compound, none of those things will affect the rate of a radioactive decay. That's sort of set in stone. There's a lot of different types of radiation, and they all have different properties like size, charge, intensity, how much damage they do. The ones that we're going to look at are listed below: alpha particles, beta particles, gamma, neutron radiation, positron particles, electron capture. We'll probably focus mostly on alpha and beta particles and a little bit about gamma, and I'll just talk briefly about the other ones. All right, what is alpha radiation? Well, alpha radiation is a stream of particles that are called alpha particles. So we have alpha particles, and they are emitted from the nuclei of unstable compounds, and a stream of them then are directed at directed out of that compound. Alpha particles are very small, and they are identical to a helium nuclei. They have 2 protons and 2 neutrons. So you can see usually what happens is you've got a big nuclei with lots of protons and neutrons, and if it's unstable, a lot of elements will shoot out a small particle that has 2 protons and 2 neutrons, which we call an alpha particle. And we can represent an alpha particle by the symbol that you see here, alpha. Or we can write it in with our nuclide symbol with the helium and the 4/2, 4 being the mass of the nuclei, and 2 being the number of protons, the atomic number. We are going to review those little nuclide symbols in just a few minutes, if you've forgotten them. All right, beta radiation is a stream of beta particles. A beta particle is identical to an electron, however, it comes out of the nuclei rather than surrounding the nuclei. So it's shot out of the nuclei of an atom when an atom is unstable. Usually what happens is that there are too many neutrons, and so a neutron will spontaneously convert to a proton, and as part of that, it will shoot off an electron because the charges need to stay balanced. So it converts a neutron into a proton and a beta particle, and the beta particle then is shot out of the nucleus and comes out of the compound, the element. Beta particle, again, now they're very tiny because they are just like an electron. And we can represent the symbol for a beta particle, as you can see down here, a beta symbol, which is the Greek symbol beta, or an E for the symbol with a -1 as the bottom number and a 0 because it doesn't have any mass. And that -1 is kind of weird, but you'll see how that works in a few minutes. Okay, gamma rays. Gamma radiation are just high energy radiation. They're rays and they are not particles at all. Again, if an unstable nuclei undergoes sort of a rearrangement of its particles, and it gives a more stable nucleus. And then when they do that, energy is just shot out of the nucleus. Now this time, again, no particles, no mass, no charge associated with it, just high energy. So the symbol for gamma is the Greek symbol gamma, which you see there. It sort of looks sort of like a funny V. Or sometimes we also represent a gamma particle with its mass and charge 0, 0, because it doesn't have any mass or charge. Neutron radiation. A neutron radiation is a stream of neutrons, and so a neutron can be shot out of a nucleus. So here you see on the right, if you have beryllium-13, which has 4 protons and 9 neutrons, and then it will, if it shoots out a neutron, now it has 4 protons and 8 neutrons, and it's a little more stable. A neutron, it has the symbol, as you can see here, a little n, and it has no charge because it's neutral, but it does have a mass of 1. Remember that neutrons are the same size as a proton, and they have a mass of 1 AMU. So that's the symbol for a neutron. Positron. Positron radiation is a stream of particles called positrons. And positrons are actually identical to electrons in size, but they have a positive charge instead of a negative charge. So they look just like electrons, but they're positively charged. And they're created similarly to the way the electron or the beta particle is formed. This time, a proton is converted to a neutron, and a positron then is sent out. So this time, if you've got too many protons with respect to, in a ratio with the neutrons, then some of the protons will convert to neutrons and send out a positron particle. The positron particle are given the symbol is very similar to a beta. We just have a beta symbol with a positive sign next to it. Sometimes the positive sign is superscripted as well. Or we can see, you can write the symbol electron, however, as a positive one on the bottom rather than a negative one. Okay. The very last type of radiation that we'll talk about is called electron capture. Electron capture is actually, radiation. It's not really a particle. Electron capture happens when the nucleus is unstable. It grabs an electron. You can see an electron on that first ring. It grabs an electron and drags it into the nucleus because it needs to. It's sort of the same thing. It'll take a proton and convert it to a neutron by grabbing an electron. Then what happens is that lower electron is no longer there, and so some of the higher electrons will start to fall down to lower levels because they want to be at a lower energy. So as these electrons fall down to lower energies, they give off a stream of, it's not really a particle, but it's a stream of high energy, similar like a gamma ray. It's just high energy. All right, so this is a nice little summary of the different types of radiation. So alpha is like a helium nuclei, and you can see some of the different symbols that you can use for alpha. There's some of the symbols for beta, gamma, a neutron, and a positron. And then you can see what the charge is, what the mass number is, and a little bit of a description of what's happened. So this is probably a good thing to come back and look at later on. All right, so like I said, we're just going to do a short review of nuclide symbols. What we want to be able to do is write a nuclear reaction. Nuclear reactions are a little bit different from normal reactions because we have to keep track of the charges and the masses. So you may or may not remember these nuclide symbols, but the X represents the element symbol. So like if you're talking about carbon, it would be a C. If you're talking about oxygen, it would be an O. Whatever the symbol is in the place of the X. Z, which is the atomic number, which again is the number of protons, and that's usually the whole number, which is the usually found on the top of the element in the on the periodic table. So for carbon, the number of protons is 6, so little z would be 6. And then A is the mass number. And remember that the mass number, because protons and neutrons both have mass, the mass number is the total of the number of protons plus neutrons. And again, keep in mind that different elements can have different mass numbers. I mean, the same element can have different mass numbers, and we call those isotopes. If they have the same number of protons but a different number of neutrons, it also means they have a different mass number, and so they are called isotopes because they're still the same element. And these numbers, remember that the number on the periodic table, that is sort of the decimal number that has a lot of decimals, point whatever, below on the bottom of the periodic table, that is an average of all the isotopes. So we're not using that number for this chapter. We're using a whole number, mass number, which will be the value for A. And we'll do some examples in just a minute. Okay, so let's just do a few examples. Write the appropriate symbols for the following. So americium 241, 241 is the mass number. If we look up americium, it is symbol AM and has 95 protons. So the complete symbol for americium 241 would be the symbol AM, the bottom number would be a 95, and the top number would be a 241. Remember that the 241 is made up of protons and neutrons, so if you wanted to know the number of neutrons, subtract 95 from 241 and you get 146. But again, the top number should be the 241. All right, a positron particle, we just saw that a minute ago. It either looks like a Greek symbol beta with a positive 1 on the bottom and a 0 on the top, or you could also use the symbol E with a positive 1 on the bottom and a 0 on the top. An alpha particle is a particle that has 2 protons and 2 neutrons, and so the 2 is the bottom number, 4 is the top number, 2 plus 2 is 4, and you could either use the symbol He, which is helium that has 2 protons, or you could use the symbol alpha. Either one will work just fine. Okay, uranium 238, well, again, we'd have to look up uranium, and we find that uranium is element number 92. It has 92 protons, so 92 is the bottom number, and 238 is the top number. And then you use the symbol U. Again, if you want to find out how many neutrons you have, you would subtract 92 from 238 to get 146. Okay, finally, the particle that has 53 protons and 78 neutrons. Well, the element that has 53 protons is iodine. So you would put the symbol I with 53 on the bottom, but now be careful here because remember the top number should be the total of the protons plus the neutrons, and so if you add 53 and 78 you get 131. So that is the symbol for these elements. All right. Okay, so what we want to do while we reviewed those nuclide symbols is that we want to be able to write an equation for a nuclear reaction. So if you have an unstable nucleus called the parent nucleus, it will undergo radioactivity or undergo radioactive decay. And when that happens, usually what's happening, not always, but usually what's happening is that the number of protons is changing. So you often have a new element. And we call this new element, or the product of a radioactive decay, we call that the daughter nucleus. Okay, so what we're going to do is write the equation by putting the parent nucleus on the left side of the arrow, and then the daughter nucleus on the right side of the arrow. And then other symbols are added depending on the reaction. So if it's a beta emission, then a beta symbol will be there, or alpha. And also you can figure out, if you don't know what it is, you can figure it out because the equation has to be balanced. And the way that you balance a nuclear equation is that the sum of the atomic numbers, which is the bottom number, the sum should be the same on the left side of the arrow as it is on the right side of the arrow. the bottom numbers. And I'm going to show you an example of this in just a minute. And then the sum of the mass numbers on the left-hand side of the equation also has to equal the sum of the mass numbers on the right side of the equation. And the mass number is the top number. Okay, so let's look at an example. Samarium 148 undergoes radioactive decay, and the daughter produced is neodymium 144. So you can see the equation on the bottom. You sort of imagine that I don't have the alpha particle there, and we can figure out what that particle should be by balancing the equation. So I put the samarium 148 on the left, and if we look up, samarium is element 62, so it has 62 protons. And then we put neodymium on the right, and neodymium has 60 protons and a total of a mass number of 144. So the alpha particle with an atomic number of 2 and a mass number of 4 balances this equation. So 148 going to 144, you would know that it has lost a total mass number of 4. The 62 protons decaying to 60 protons means that it had to have lost 2 protons. So notice that on the left-hand side we have 62 on the bottom number, and the total of the numbers on the right are 62. We have 148 for the mass number on the top, and 144 plus another 4 to give us 148. So the balanced equation has an alpha particle. Here's another example. Bromine 84 decays by emitting a beta particle. Write the equation for this decay. What is the symbol and name of the daughter nucleus? Okay, so let's start out. We know that the bromine 84 has the symbol Br. Bromine has 35 protons, and it has a mass number of 84. Again, we don't need to know the number of neutrons in this case, but we could figure it out. It is 84 minus 35 is 49. But in this case, all we need to know is the mass number and the atomic number, 35. All right, and then the one thing we know is that a beta particle is emitted, so it's given off. So that's on the right-hand side of the arrow. Now, a beta particle we know has a mass of 0, because it doesn't have any mass, and it has a charge of -1, so it's like an electron. So we can represent this. You can see that as -1, 0 with a beta, or -1, 0 E. So on the lower equation, you can see I've put the Br 84 on the left-hand side of the arrow, and then the -1, 0 beta on the right-hand side. So what is the daughter product? Well, it needs to be whatever will balance this equation. So since a beta particle has no mass, the new particle, the daughter particle, has to have the same mass as the bromine, so 84. So 84 plus 0 gives you 84. The top numbers are balanced. Now the bottom number of the new element has to be added to -1 to give us 35. So 36 minus 1 will give us 35. Or you can think of it as -1 plus what will give you 35? Well, it's 36. So 36, the element is krypton, and so we put that symbol, Kr. If you remember earlier, what I said, a beta radiation is changing a neutron to a proton. And so if you look at the numbers, we said that bromine has 35 protons and 49 neutrons, and now krypton has 36 protons, and the mass is the same, so it now has 48 neutrons. So in fact, that's exactly what happened. A neutron has been converted to a proton, and a beta particle is given off. So anyway, 36 plus a -1 gives us 35. All right, here's one more example. An electron capture is not giving off an electron, but it's grabbing an electron. So the tungsten 175 decays by drawing in an electron from outside of the nucleus in electron capture. Write the balanced nuclear equation for this process. So in this case, the electron is actually a reactant because the nucleus is grabbing it and adding it to itself. So here we have tungsten 175, and if you need to know the bottom number, you look up the element tungsten, and that's element 74. And we add an electron to it. Now notice that the mass number again doesn't change because an electron doesn't have any mass, so it's still 175 on top. But this time, 74 plus a -1 gives us 73. So in this case, actually, a proton has been converted to a neutron. And so again, the only thing you have to worry about is balancing the bottom numbers, and then you find the symbol that matches. So the element 73 is tantalum, Ta, and so this is our balanced equation. All right, so let's go through a few examples. You might want to look at it, stop it, and go through these examples and figure out what the answers are, and then come back and listen to me. Of course, the answers are on the next slide, but let's just talk through them. All right, so balance the following nuclear equations. That top one, cobalt 60. Cobalt has 27 protons, and then it has 33 neutrons. Anyway, if it's giving off a beta particle, the bottom number needs to be whatever you add to a -1 to give us 27. So it has to be 28. 28. What element is 28? It's nickel. So the bottom number is a 28. Nickel is the element. And then what's the top number? Well, whatever adds to 0 to give us 60. So of course that's 60. So so cobalt 60 has converted to nickel 60 and given off a beta particle. All right, moving over to the right, radium 236. If it becomes radon 86, what's happened to it? Well, you can see 88 is its original number, and afterwards it's 86. So what's happened? Well, it had to have given off 2 protons. So the bottom number for what we're looking for is 2 protons, a 2. We see that the top, if we subtract 232 from 236, is 4. So the top number is 4. And of course, what's the symbol for 2 protons? It's helium. Or you also remember it's an alpha particle, so you could use either He or an alpha symbol. Okay, how about the left, the xenon problem? What do we start with that will give us a positron emission and the daughter be xenon 131? Well, again, just make sure that you balance your bottom numbers and your top numbers. So we've got 54 plus 1 on the right hand side. So what's on the left hand side? 55. 55 is element cesium. Okay, so we would have 55 on the bottom, cesium is the element, and then 131 on the top, because 131 plus 0 is 131. Okay, finally, potassium 40. If it does electron capture, now the top number doesn't change, so the top number on the right hand side of the arrow will be a 40, but 19 plus a -1 will give us 18, so the new element will be argon. So argon, Ar, 18 on the bottom, 40 on the top. Okay, so that's sort of filling in the part of the nuclear equation. How would we write a complete nuclear equation? Now, the above ones, I could have you fill in anything, but I will only ask you to write a balanced nuclear equation for positron, alpha, or beta. I won't ask you to write one for any other from scratch. All right, so a positron emission of manganese 50. Well, first of all, what's the symbol for manganese 50? Well, manganese, which is Mn, is element 25, so the bottom number should be 25 and the top number should be 50, and the symbol is Mn. All right, it's a positron emission, so we write the arrow and then we write a positron. Well, the symbol for a positron is the same as up in the xenon equation up above. It's a beta symbol with a 1 and a 0. So what does the other daughter product have to be if one proton is broken off of the manganese? Well, since it was a 25, 24 has to be the product, because 24 plus 1 gives us 25. And then the top number, since a positron particle has no mass, the top number will stay 50. So on the next slide, you'll see that written out. Similarly, alpha emission, you start with polonium-210. Polonium is symbol PO and it's element 84, so the bottom number would be 84, the top number would be 210, and the symbol is PO. Then on the other side of the arrow, since it's an alpha emission, the symbol for an alpha particle is a 2 on the bottom, a 4 on the top, and either helium or alpha. And then what will the other particle be? Well, 2 plus what gives us 84? The answer would be 82. What is symbol 82? It is lead, Pb. What's the top number? Well, what plus 4 gives us 210? The answer would be 206. So the top number is 206. All right, one more example. The beta emission of Pa-231. I don't even know what Pa is. I'll have to look that up. Anyway, if it's giving off a beta particle, that means the bottom number is a -1, the top number is a 0 with the beta symbol, or it could also be the E symbol. So what other daughter product will we have? Well, what plus a -1 gives us 91? Well, don't get confused here, but make sure a -1 plus a 92 will give us a 91. So the new element will be element 92, which is uranium. The top number, because the mass doesn't change with a beta particle, will still be 231. So here are the answers to what we just discussed. And again, it kind of was a lot of talking, you want to make sure and go back and make sure that you understand how these work. All right, one other topic that we're going to talk about is the half-life. If you have a sample of radioactive compound, all the nuclei are unstable, and at some point they will decay. The problem is we don't know which one's going to decay, and we don't know how they're going to decay. They won't all decay at once. They're going to decay at different times, but the thing is that they have a fixed rate of decay, and we call this the half-life. So what is a half-life? Just like the name implies, it is the time required for half of the radioactive nuclei to undergo decay. It doesn't matter how much you start with. However much you start with, after the certain amount of time, half of the nuclei will decay. So if you started with, say, 100 grams of something, after the half-life, you would have 50 grams left. Then actually, since you start with 50 now, after another half-life, you'll have 25 left. And then after another half-life, you'll have 12 and a half. So it keeps going, because it doesn't matter how much you start with, it will keep half, 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 half. And one thing to keep in mind is that the half-life of an isotope can be used to indicate the stability of an element. If you have a long half-life, that means the isotope is a bit more stable. If you have a very short half-life, that means it's a very unstable element or nucleus. Now, the important thing also to remember is that a half-life cannot be sped up or slowed down. It just is what it is. So here's sort of what I was just talking about. So let's say we started with 100 grams, you could think of it as grams or percent, 100% or 100 grams of cobalt-60. Cobalt-60 has a half-life of 5.3 years. So after one half-life, which would be 5.3 years, half of all of that cobalt will have decayed. So we'll only have 50 grams of the cobalt left. Now the rest of it doesn't disappear. Remember that we produce the daughter, so we'll have 50 grams of the daughter material. I'm not sure what that is. We can do that in just a second. All right, but then after two half-lives, if we started with 100, after one half-life we go to 50. After two half-lives we go to 25. So that's half of the first half. And since it's two half-lives, that's 10.6 years. So now we have 25 grams of the cobalt and 75 grams of the daughter. Okay, 12.5 grams after another half-life. So after three half-lives, we've gone down. So we've gone down to a half, a quarter, an eighth, which is 12.5 grams. is left. That's after 15.9 years, which is 3 half-lives. And then after another half-life, so after 4 half-lives, which is 21.2 years, we'll have 6.2 grams left. After many, many half-lives, now technically speaking, you never get to 0, but because we're talking about a particular amount, eventually it will get so small that we won't be able to detect it anymore. So we kind of assume that it gets down to 0 after so many years. So I don't remember. Oh yeah, we looked at that earlier. Cobalt-60, when it decays by beta, it actually decays by beta decay, and that's on one of the earlier slides. And so the daughter is nickel-60, and so you notice that the amount of nickel keeps increasing, the amount of cobalt keeps decreasing. But cobalt is the one that is unstable, and nickel is not. So the nickel will hang out. So here's some examples of half-lives. Uranium-238 has a half-life of 7.1 times 10 to the 8th year, so that's almost a trillion years. It goes by alpha or gamma radiation. It is often used in nuclear reactors. You've probably heard of uranium-238. And that is a natural isotope. Potassium-40 has a half-life of 1.3 trillion years. We use potassium often to date rocks. It's also a natural isotope. Radium-226 is another natural isotope that has a half-life of 1,600 years, and it mainly goes by alpha radiation. They'll use this a lot of times to it was used in luminescent paint, but it's because it's radioactive, they don't use it anymore. All right, carbon-14 is another natural isotope where the half-life is 5,600 years, and it is often used in archaeological dating, and so you can date, I think we'll talk about that in a little while in this chapter. Okay, here's some synthetics. So a lot of isotopes can be made. Americium-241 has a half-life of 433 years, and this is often put into smoke detectors, believe it or not. Phosphorus-32 has a half-life of 14 days, and it is often used in leukemia therapy. And iodine, that's a real important one. Iodine-123 has a half-life of 13.6 hours, and often it's used in thyroid therapy. And later on in the unit, we're going to talk about medical uses of radioisotopes. But what I wanted you to see here is that uranium is probably potassium-40 would be the most stable out of all of these because it's got the longest half-life. So it's not in a hurry to decompose, but it's still unstable enough that some of it will decompose over time. Now phosphorus with a half-life of 14 days is kind of on the right amount of time to use in the body, because after so many half-lives it'll be gone from the body. Similarly with iodine-123, if it's only has a half-life of 13.6 hours after maybe 4 or 5 half-lives, which would be on the order of 2 or 3 days, it's totally gone from the body, which is what you want. Now oxygen-15 has a half-life of only 2 minutes, so it's really unstable, and lithium-12 has such a short half-life, it's not even useful. We can do half-life calculations. There's actually some formulas that you can use, but the only half-life calculations we're going to do are simple ones. And what you can do is, if you're given, let's say you know how much is left over, you can figure out how many half-lives it took to get there, or you can figure out how long a half-life is, and so how many years did it take to get to a certain amount. Because remember that every time you go through one half-life, you have half of the material left. So after one half-life, you've got half. After 2 half-lives, you've got a quarter, or 0.25. After 3 half-lives, you have an eighth, or 12.5. After 4 half-lives, you have 1/16, which is 6.25, etc. Oops. Okay, let's look at one more example. So a radioisotope has a half-life. Now we know the half-life, a half-life of 20 days. How long will it take to get 1/16th of the original sample to be left over? All right, so it's sort of similar. How many half-lives is it to go from 100% down to 6.25% or to 1/16th? Well, after the first half-life, you will have 50% left, or 1/2. After a second half-life, you'll have a quarter left. After a third half-life, you'll have an eighth left. And then after a fourth half-life, you'll have 1/16th. So it takes you 4 half-lives to go from 100% down to 6.25% or 1/16th of the original sample. So if one half-life is 20 days, how many days is 4 half-lives? Well, 80 days. So you would need 80 days for this to go to decay by 4 half-lives. All right, so that's the end of this this slide, the YouTube, and we'll finish it up on the last one.